and that's what really increases the price. It doesn't require those expensive catalysts. Ultimately, put it in that machine to make it flat, and that's how you get
Yes.
the membrane. And continually try to improve it as we try to bring down the cost of hydrogen and make it widespread.
How do protons actually make it through a membrane, even though it doesn't look like it? These are some of the questions I'll be looking at today when we're talking about membranes for applications in the hydrogen economy. I have an expert joining me today from HyProof, and I'm very happy to welcome Tim Wu. Hi, Tim.
Hi, Stephen. Nice to meet you, and thank you so much for introducing me here. I'm Tim from HyProof, and we're going to here talk about membranes and how it works in the hydrogen economy.
Absolutely. I know you guys have been doing this for about a decade, so lots of knowledge there. But let's start from the basics. Tim, what exactly is a membrane?
Thanks. Great question. Membrane in the hydrogen economy is sort of where the magic happens. In the fuel cell and electrolyzer, it's what separates the gases, and water, for what's needed in the hydrogen economy. In the electrolyzer, water and oxygen and hydrogen, and same thing with the fuel cell in reverse.
So basically, what's between these two and what then kind of enables or allows the reaction? Yeah.
Yes, exactly. So
Okay.
the membrane along with the catalyst will cause the reactions to occur, and that's how we produce hydrogen.
Okay. I see you have a slide to show that as well.
Yes. Yep. So here, as we can see, overall on the left, you can see a membrane, which is things that are produced by many manufacturers. But on the right, you can see electrolyzer. Electrolyzer, you have the membranes in between each stack. And then that's where water will go through and then be split into hydrogen and oxygen. You capture the hydrogen, and then you're able to then go to use that as fuel for something like a fuel cell. You use fuel cells in cars, and then you use that to generate electricity in order to power whatever you're trying to power.
So you have them in fuel cells and you have them in electrolyzers. Can I use the same type of membrane in fuel cells as in electrolyzers?
They're the same type of material, but typically you want fuel cells to be a thinner membrane and electrolyzers to be thicker because the electrolyzers go through a lot more pressure gradients and differences. Also other different things where the membrane needs to be stronger. Fuel cells more so just to generate electricity, and you want efficient electricity generation. So you just want it to be thinner there.
Okay, so you use them in fuel cells and electrolyzers. Those are the main applications in the hydrogen economy. Okay, and yeah, please.
There are a few other examples where we can use it in other applications in the hydrogen economy. I just want to show on this slide. There's companies who are trying to take carbon dioxide and convert it back into jet fuel. And so you use membranes like that to selectively separate carbon dioxide, in addition to the membranes used for electrolyzers as well. So, and then one other thing was just flow cell batteries. It's an older technology, but you also use the membranes for that as well. It's a safer way than lithium for industrial purposes, but that's just one of the examples of what membranes can be used for also in the hydrogen economy.
Okay, but do I understand correctly that your focus is much more on the hydrogen application, so not these ones, or you do that as well?
Yes, we do those as well, but we're going to focus here today on for electrolyzers and fuel cells. Yep.
Okay, perfect. Okay, right. So I know there are different kinds or types of membranes. Can you help us and educate us what types they are?
Yes, of course, definitely. So in the current market now, there are 3 different types of membrane materials. The oldest being alkaline. That was used a while ago and is still being used by some of the electrolyzers we see today. But more of the hydrogen economy is now pushing towards PEM usage. And then also we're starting to see a shift towards AEM, which is anion exchange membrane usage. Each has its pros and cons, which I would love to go into over here.
Yeah, please.
Of course. So with alkaline, it's the oldest technology. The way it works is water goes in, and then hydrogen actually stays on this side, and the hydroxide goes over and becomes oxygen on the other side. With this being an older technology, it's usually a diaphragm, that type of membrane. So I sort of rated it lower safety because the problem is it's with being such a higher pore size, hydrogen can potentially cross through, which is something that we don't want. When H2 and O2 combine together in midair, that can cause an explosion. And so we
Yes.
don't want that to happen, and which is why we say that this is sort of old technologies that should be sort of pushed away.
All right. Okay.
And in terms of cost also, it's been around for a while, so the cost of alkaline membranes is not that expensive. But one downside about it too is it needs constant power for it to run properly. Any fluctuations in power it causes us not to generate hydrogen as well as it needs to compared to the other two.
All right. Okay. So just to understand, I mean, what you're showing there basically is a cross section of the cell, you know, with the anode and the cathode being the, let me say, the current bearing part. So, you know, electricity being pushed through there basically, and then you have the water on the one side, and then the hydrogen which we're trying to generate comes up at the top, and the oxygen mixed with some amount of hydrogen comes out on the left side.
We moved on to most folks are trying to use proton exchange membranes, which you see mostly in the market now with the different fuel cells and electrolyzers.
Yes.
The way this works is a little different. The water comes in, oxygen actually stays on this side, and then as it hits the anode, the hydrogen goes through and reaches the other side. It goes through as a proton, and then the electron goes through on the other curve, and then comes through on the other side as hydrogen here. So here there's a lot of pressure buildup with the hydrogen, but with the newer technologies, we're able to adjust the pore size of the exchange membranes to the nano size so that you're able to prevent hydrogen from crossing back over from all the pressure buildup with it building up.
Okay, so I know we're getting closer and closer to understanding what a membrane is, but I mean, for those of us who didn't pay all the much attention in chemistry class, what's the difference between a membrane and a diaphragm, please?
So it depends on what it is. So a membrane, it'll separate things out. Same thing with a diaphragm, but the way you call it a diaphragm because the pore size was much larger.
All right.
It's not as I guess finessed compared to the current technologies as there are today. So we just call it diaphragm. Just means like the pore size is much larger. So the potential for more hydrogen crossover.
Okay. Okay. Cool.
Different material as well. So
different. Okay. Thank you.
And then in terms of safety, since we're able to adjust the pore sizes to the nano size and also add different catalysts to prevent hydrogen crossover, we make it much safer today. And also in terms of fluctuations of power, it's able to withstand, if you're using solar to split the water, it's able to withstand those fluctuations.
All right, so there you can, you know, the current or the power can go up and down, and PEM is more or less fine with that.
Yes, exactly.
All right.
But one downside that we're all seeing is the anode and cathode, which required very expensive catalysts such as platinum and iridium. That it can be very, very expensive, and that overall adds to the costs of a hydrogen electrolyzer, and which is one of the downsides of PEM. It's really expensive to get those precious metals, and that's what really increases the price, which everyone's trying to bring the price down of hydrogen so that it can be more economical and then more widespread use.
Understood.
Which sort of also brings me then to anion exchange membrane. The anion exchange membrane sort of takes best of both worlds of alkaline and PEM. And so it processes similar to the way alkaline does, as you can see here. Also use pure water. But also it doesn't require those expensive catalysts that PEM requires. And also the anion exchange membrane is now adjusted for that pore size so that it can prevent hydrogen crossover as well. So overall rated the safety is really high with a low hydrogen crossover. It's relatively cheap as you don't need to have those expensive catalysts. You can use things like nickel or iron. And then also in terms of fluctuations, it's able to withstand those fluctuations as well that we talked about earlier.
Okay, so following this simple diagram, there's an absolute case for the use of AM.
Yes, exactly.
Right.
So a lot of companies are trying to look into that, and we've created our own AM and continually try to improve it as we try to bring down the cost of hydrogen and make it widespread.
Okay, and so is there a reason for choosing any of? Okay, I mean, obviously, I guess since you are making the AM one, you will see more of a case for AM. But I know there's quite some companies out there also doing PEM electrolyzers. What reasons do they have?
A lot of the reasons they have is initially PEM did come out first before AEM.
Yeah.
So most of them still find that it's still worth going through with PEM. A lot of them have put a lot
Understood.
of research into it and have sort of developed that technology. Again, the limiting factor with it is the precious metals. It's rare to get these type of precious metals, and it's just very costly. So unless
Hmm.
somebody can start creating these precious metals at scale, it's we're seeing folks starting to look into the AEM space as it is
Yeah.
similar to the alkaline, and it's again takes best of both worlds from the alkaline and PEM membrane.
Okay, I'm going to ask you in a moment how exactly it works in the membrane, but before that, the AEM membranes, what is in there? What material do you need to make such a membrane?
Yep, I can go into that. We'll go into that a little later too, but for the way we make it is a little different from the way other manufacturers make it. We use an ePTFE backed membrane, and then we add our own different so there's the resins to it in order to make that membrane work.
Hmm.
Different formulations is what we make, and I can get into that slides later as well.
Okay, cool. Well then, now I want to know, how does a proton get through there, or and whatever it is that is going through. I see you have a hydroxide in your diagram. How does it actually work now in the membrane?
Of course, let's take a look. Let's actually go into how it works in an electrolyzer. This just wanted to show this here because this is maybe what you've seen in science class, with
Hmm.
your professor using some type of beaker with water in there, and you see bubbles coming
Hmm.
out. But let's
Yeah.
go to an actual real life use to answer your question.
Yeah.
With the fuel cell, you want to ask how the proton goes through. So
Yes.
I'm going to use my mouse here. So this is a
Yes.
fuel cell, so hydrogen will come through. And then as it hits the catalyst layer, which is one of those platinum or iridium-based catalysts, the electrons
Yeah.
will bounce off, and then hydrogen only becomes a proton. So as it hits this membrane, it'll then only go through as a proton. The electron will bounce through, go through a different conduit, power
Hmm.
whatever you're trying to use, a car or a light bulb.
Hmm.
And then the hydrogen and the electron will then, the proton and the electron will then combine back together and then hit the oxygen in the air and then form water, thereby not having any CO2 emissions, which is what we would like to see, and which is one of the mainstays of the hydrogen economy.
Hmm. So, as I see this, the actual magic is that the catalyst, once the hydrogen comes near that catalyst, it has this, it's more or less forced, or has a, what happens? Why does it split off the protons actually? Is it hot, or what happens to it that it decides to do that? I mean, I understand the catalyst does that, but why does it do that? And then it permeates through the membrane, right?
Yes. So the precious metals or the catalyst will be what causes with will be what when it hits it, that's what
Yeah.
it'll cause it to split, the hydrogen to split with the electrons can't go through, and that's
Yeah.
part of how it works. So it forces that electron to go through the conduit on the other end. And again, so it's sort of like only allowing one thing through.
Yeah.
One example I saw was really good, is similar to going through the airport terminal, where you can go through, but your baggage can't. So your baggage, like for example, your baggage is the electron, and it has to go through
Yeah.
the scanner, and then but
All
only
right.
go through. So that's an
Okay,
example.
okay. That's a good one. That's a good one. Especially, those of us traveling around a bit will know to relate to this. Okay, cool. Thanks. I know that like we've seen how this works, and so what are some of the things I should consider when choosing my membrane now? Like what are the specs that we're talking about? Like you've mentioned thickness. Is there anything else that we should look at?
Of course. So there's four things that we consider for a really good membrane,
Hmm.
listed here. The first thing would be high ion conductivity, just meaning that the amount of electricity put into for electrolyzer to split the water into hydrogen and oxygen, that you create a lot of hydrogen with that electricity. The less electricity you have to put in, the better.
Yeah.
And that's one of the that's more efficiency.
So there's membranes that need more electricity, and there's membranes that need less electricity.
Yes. Yep.
All right.
So it
Okay.
just depends on how it is, how you make it.
Yeah.
Also depends on the catalyst. So there's a lot of different factors, but the
Sure.
membrane is one of them that causes
Sure.
that reason. Yep.
Yeah.
Next thing would be low hydrogen crossover rate, which is more of the safety piece. You don't want hydrogen to be able to cross over, and then also overall strength mechanically, chemically, and electrochemically, which I can go into to show in a few slides, just certain tests that are run by everyone that takes a look
So
at
this is like real like physical strength, like will it stand the pressure, that kind of thing. Okay, so can
Yes,
I
that's
put
correct.
like, whatever, 20, 30 bar on it?
Yes,
Okay, that kind,
exactly.
understood.
Mhm.
Yeah.
Yep. Yeah. So let me actually show you some, for example, for our AEM water electrolysis, we have our ion
Yes.
curve here. So the flatter the curve, the better. That just means
Mm-hmm.
that you have a better ion conductivity. This is just an example of a test that we had done with one of our membranes. And then to continue, we take a look at that as well. High ion conductivity with our PEM membranes. The flatter the curve, the better. That just means that you're able to produce more hydrogen with less electricity being input.
So this is showing the durability, meaning that it'll just, be same output over time. Okay. And what we
Yes, yep.
got?
Just
Okay,
on the
so we
left
got like
side,
two.
so
Mm-hmm.
yeah, just electrical thermal strength. It's just we tested to just make sure that over thousands of hours, you can see here to see if
Yeah.
there's voltage difference or how strong it'll last throughout the durability. So
Right, right.
that's very important. So it's when customers want to, or people want to buy the membranes for the electrolyzer or fuel cells, you want to make sure it lasts quite a long time. So which is why you do
Okay. So
thousands
so
of
how
hours.
long does a membrane last? I mean, yeah, the chart goes beyond 2,000 hours, but can I also operate it for 5,000 hours?
Yes, so we continue to keep testing, and I know it's relatively new, but we estimate anywhere probably close to around 10 years is how long it'll last for our membranes, the ones that we make. So,
Okay, right. Okay. This probably also depends on, the operating conditions and if your system is
yes,
treating them nicely. Okay.
yes, yes, that's true as well. And so going into that, there's other tests, the chemical strength tests, and then also electrochemical, as we talked about. Here, as you can see on the left side, with our AEM,
Hmm.
we have it in acid actually. So with our competitor membranes, we see that it starts breaking after a few thousand hours. And
Hmm.
then we also have ours here in the red, which shows that after the other three broke, ours was still standing. Um, things like that, because there's different situations where you would use the membranes. It could be in saltwater electrolysis where you have different chlorine gases or things like that that's going to affect it. Or if you want to have an acid. So different situations, just you want to make sure that your memory can last through all of that.
Okay, so basically, when you're talking, like when there's other chemicals or things around, but I mean, in an electrolyzer, does that really happen? I mean, aren't you feeding, more or less some kind of purified water to it, and then just, expecting the hydrogen and oxygen? I mean, do you get any acids in there?
So sometimes we do try to use clean water, but sometimes folks want to use something different. And
Yeah.
also, you do have it in a little bit of a alkaline structure, water that runs best, the most efficient.
Hmm.
So it has to run at some type of alkaline solution.
Uh-huh. Ah, okay.
That's where
Okay.
you find it. It runs better in those type of solutions. So you just want to make sure that it
Understood.
can last in there.
Okay.
And then also just on you see on the right, there's swelling rate as well. There are some membranes, how they're made, they may swell a lot. So that
I
sort
get
of
thicker.
affects how you're gonna put it in. So sometimes you have to activate the membrane, swell it up. With ours, we tried to make it so that you don't have to do that. And the swelling rate is very, very minimal, as you can see here with our anion exchange membranes. So, you
Understood.
have other competitors that make it differently and just want to show that it does swell. So you always have to make sure that however whichever product you're using, you want to make sure you know whether or not how to activate it beforehand or if it needs so, because that's where some customers may run into issues.
Yeah. Okay. Got it. Got it.
And then, as we talked about mechanical strength, we do this like a little testing here. When hydrogen, for example, when you use the electrolyzer, the hydrogen buildup is going to push back. So
Hmm.
you need to make sure that it's able to withstand that force to push back on the membrane.
Yeah. Yeah.
So that's why we have these testings that are done, whether it be megapascals or other things. So you need to make sure that tensile strength is at least 35 or more for bars or
Okay.
pascals.
So
Yep.
this is like really, old school mechanical tensile strength.
Yep. Yep.
Okay. Okay. Okay.
Exactly.
Swelling rate, conductivity, chemical resistance. Okay. So I'm getting them, and thickness. Okay.
Yes,
Okay.
thickness as
Hmm.
well. Yep.
Hmm.
So for electrolyzers, you want them to be thicker. because it has to withstand the pressure from the hydrogen that's been created that's pushing back. So
Can I mean, so don't these like, kind of, what did I say, rule each other out, So I like, okay, I need a thicker one, so that's fine, I get a thicker one, but that means my conductivity is going to go lower, or isn't this like a kind of balancing game that you have to play?
yes, exactly. So when we working with folks, it's just depending on how your apparatus is, it's like you can get something stronger, something thicker, but then yeah, your efficiency is going to be less. But it's like where do you want to balance? So
Yeah,
sometimes you want it a
yeah.
little thinner, have more efficiency, but then the membrane may not be as strong. So
Okay, understood. Okay, and I see you have some test standards that also apply. So I guess these are these global, or especially relating to high proof?
for us, we find that this has sort of become the standard. Hydrogen is sort of a little wild, wild west type thing where there's standards being set still in motion.
Yeah, yeah,
We're trying to get to that standard. And everyone's try to compare to each other now when you compare different membranes or different different products in the hydrogen industry. So
okay. So yeah, so that thank you for showing us all these different kind of specs. I think, I mean, okay, we're probably not going to memorize all the numbers now, but people can still read up on that. We'll put some of the stuff in the notes of the video. Very quickly, Tim, how do you make these membranes?
yeah, that's a great question as well. Let's get into that. For membranes, the way we make it here, high proof, what we use is actually ePTFE, which is
Mm-hmm.
our core, originally our original technology. ePTFE stands for expanded polytetrafluoroethylene.
Uh-huh.
You can just know
Yeah,
just like a mesh or some type of
yeah,
membrane that's very strong, or you can use a
yeah,
different type of mesh. But essentially, as you can see here, you take that membrane and then you add it with resin. So this is for a proton exchange membrane, and
yeah,
just embed it in there, and then under a lot of pressure and all whole different machineries, you're able to then create these beautiful rolls of proton
yeah.
exchange membranes, which then folks we can cut for to add into the people's electrolyzers or fuel cells, or they can cut it themselves as well. But here we have the ultra thin reinforced ion exchange membrane, proton exchange membrane, which is so it tries to make this easier. And this plus this equals that.
I like how you made it super simple. I mean, like, so the one is a nano fiber. So
Yes.
it's like a cloth, or
Yes.
something like that,
Yeah.
right?
Yeah.
And then the other one is a resin. What is the resin? Resin is like
It's like a powder,
it's like a
similar to
powder.
like
All right. Okay.
flour, yeah. And I
Yeah.
tried to equate
Okay.
it to some type of making spaghetti.
All
Uh,
right.
you make your dough with your eggs, flour, and everything. And that's
Yeah. Yeah.
like the
Yeah.
flour part. And so, and you ultimately put it in that machine to make it flat, and that's how you get
Yes.
the grain. Yep.
Yeah. Okay. Okay. The great analogy that. Okay. Perfect. Perfect. Yeah. No. Cool. So where do you then? So you make the membranes, and then who are the people who use this typically, or who want to buy this?
Yep. So it's usually those who are in the electrolyzer or fuel cell industries.
Yes.
Those
Yes.
who are making electrolyzers, they're selling electrolyzers. They need these membranes in there, and
Yeah.
so there's multiple manufacturers, but we're just one of them. And then so they test they test membranes and they see whatever works best for their setup.
Right.
Go
Right.
with that, and that's what they sell. So
And
we
and
sell
and and
them
and
into fuel
you
cells.
able? I know you on the one slide you showed the three different products that you have, but are you able to still variate or customize your membranes if someone wants them? There's still a little bit thicker. You guys still able to do that?
Yes, definitely.
Yes. Yes.
So
Okay.
they
Great.
ask that question all the time. Can you customize for us? And yes, it's very easily
Yeah.
customizable for us to increase and decrease the thickness that you need. Overall,
Yeah.
it's the same product, whether it be used for fuel cells or for electrolyzers or for other things as well. We had someone ask for saltwater electrolysis, so that required our membrane to be on a different mesh, which is much stronger. I don't
Yes.
go too in depth into it, but yeah, so we can customize different things for you as needed.
Okay, cool. So last one, just also considering time. What about the outlook? I mean, like, so where is this going? I mean, you've been doing this for about a decade. Where do you see things going with membranes? Are we still going to need them? Are they getting thinner, or adding more color, or what are trends you're seeing?
Yeah, definitely.
Yeah.
So what we again saw, we saw the different type of membranes. The technology is going to continue to advance. Hydrogen economy is going to continue to grow. And we think that currently the technology prefers PEM technology, the proton exchange membranes.
Is it?
But we
Okay.
do see that in the future, the anion exchange membranes will be preferred. As we scale up, those precious metals that are needed for a proton exchange membrane, that's going to be hard to get. So in order to scale up and make it economic, you got to take the best of both worlds from alkaline and PEM and use AEM. And that's where we think we'll be going towards.
Okay, wow. Hey, Tim. Okay, I think I have many more questions still, but we'll have to end it here. Thank you so much for taking the time, and I hope everyone who's watching also found this as interesting as I have. If you have more questions, you can reach out to Tim. We'll put his contacts in this video, but you can find people like Tim on HiFinder, where you find all kinds of stuff related to the hydrogen economy. And as you see, the products are out there and we can make it happen. So just use it. Thank you so much, Tim, for spending time talking with us about this. If you like this video, please give us a like or follow us in the channel. That'll be actually much better still, because then you'll be educated from time to time on all kinds of new stuff and useful stuff in the hydrogen economy. Thank you very much. And thank you to you again, Tim. Have a wonderful time. Thank you.
Thank you. Thank you so much, again. I appreciate it.